Steinhauer here. Welcome back. We are continuing discussion of the biggest questions that you can really ask. And those are the questions related to cosmology. And those questions are, what is the universe? How big is the universe? How old is the universe? How will the universe end? What is the shape of the universe? What is the matter contained in the universe? What are the constituents of the universe? These are the cosmological questions that we're addressing and we'll get to over the next few classes. So buckle up, here we go. First, we need to do some housekeeping. We define the relationship called the Hubble law, but there's more useful parameters that are used by astronomers to characterize galaxies. And one of those is called the redshift. We know, we've already seen that virtually every galaxy in the universe is redshifted, and Hubble's law tells us that the further away a galaxy is, the faster it's moving away from us. We can parameterize this redshift by a parameter z. And z is defined in this way: lambda obs minus lambda rest over lambda rest. This might look familiar to you. This is very similar to the radial velocity equation. In fact, if you were to remember the radial velocity equation, this was VR over c. In the radial velocity equation, VR over c is lambda obs minus lambda rest divided by lambda rest. So really, we're defining z to be observationally the recessional velocity divided by that. We can use this to multiply both sides by c, for instance, to see that the radial velocity that we infer from this redshift is in fact z times the speed of light. So let's try this equation out. We know that the H alpha line of hydrogen is normally found at 656, at least when an object is not moving relative to us. Let's say that it's seen at 1312 nanometers in a distant galaxy. What would the redshift be for that particular galaxy? Well, we can calculate this because we know z equals lambda obs minus lambda rest divided by lambda rest. The observed wavelength is that which we see it. The rest wavelength is where it should be if it weren't moving with respect to us. So we can plug those values in. The observed is 1312 nanometers. The rest is 656 nanometers divided by 656 nanometers. What is 312 minus 656? Well, I've chosen these numbers for a reason. It turns out that 312 minus 656 is 656 nanometers. If you divide that by 656 nanometers, that's even a multiplication, a division that I can do in my head. Those nanometers cancel out. Oh, and guess what? The 656 cancel out too. This is just one. So z is a unitless number. We're dividing nanometers by nanometers. So in this case, if the wavelength of the light has been doubled, if it started at 656 and it's now at 312, that's a z of 1. If it started at 500 and is now at 1,000, that's z of 1. All of them get doubled. That's the z equals 1. If you're to triple the wavelength, that would be z equals 2. If you're to quadruple the wavelength, that would be z equals 3. You can try those out on your own if you like. Okay, so it turns out that the world record for largest confirmed redshift of a observed galaxy is z equals 11.1, which is a really high number. So where would that hydrogen line that starts at 656 nanometers be in a galaxy whose redshift is 11.1? Well, we can turn this equation around. We know that z equals lambda obs minus lambda rest divided by lambda rest. Okay. I'm going to do, normally people just plug in numbers here, but it's actually more useful to solve this algebraically for the thing that you want before you plug in numbers. Sometimes things cancel out. Sometimes it makes it a lot easier to do so. And in any event, you've got an equation that you can use again if you need to solve that kind of problem again. So let's try to solve this for the thing that we don't know, which is lambda obs. We know that z is 11.1, and we know that lambda rest is 656 nanometers. Let's solve this for lambda ops. How are we going to do that? Well, we need to get the lambda rests out here. So we first need to multiply both sides by lambda rest. That makes them go away over here. Now we've got just lambda obs minus lambda rest over here. What do we need to do? We need to add lambda rest to both sides. And that will cancel them out. Minus lambda rest plus lambda rest. We will have lambda obs by itself over on this side of the equation. We can bring it over to the other side and make this lambda obs equals z times lambda rest plus lambda rest. We can even simplify this a little bit, pull the lambda rest out, and we've got a lambda rest times z plus 1. And that's even easier to deal with. So lambda obs, we can plug in equations, we can plug in our numbers now, and this is pretty easy. Lambda rest is 656 nanometers. Z is 11.1. 11.1 plus 1 is 12.1. 12.1 times 656 nanometers is 6,626 nanometers. Or if you want to multiply by a factor of 3, 10 to the 3, and raise the exponent on here, this is 6.6 roughly microns or micrometers. A micron is a 10 to the minus 6 meters. A nanometer is 10 to the minus 9 meters. And so this is not even in the visible part of the spectrum, even close to the visible part of the spectrum. This is way out in the mid-infrared part of the spectrum. So again, the farther away these galaxies are, the faster they're moving away from us. Their spectra get shifted way out past where we would even be able to see it without infrared instrumentation. Okay, moving on. What are the implications of the Hubble law? Because this is really where things get stunning and have huge impacts on the way we see the universe and how we understand it. Let's just take a look at this relationship. Here is the Hubble law. We've got, again, distance to the galaxy on the x-axis and recessional velocity or radial velocity, how fast it's moving away from us on the y-axis. And you notice it's a beautiful straight line. So the question is, let's think about one of these galaxies. Let's think about this galaxy right here. We can rewind the clock. And if we do that, what happens? Well, all of these galaxies, instead of moving away from us, are actually moving towards us. And we can even figure out how long it's taken this galaxy to get to that point, right? This galaxy is 5 megaparsecs away, and it's moving away from us at about 3,000 kilometers per second. We can do some math to figure out how long it's taken that galaxy to get where it is if it started from where we are. Or conversely, we can turn it around and say, if we move time backwards, how far in the past do we have to go before this galaxy is right where we are right now? And we get a number. A big number. These galaxies are really far away, but still a number. Let's now think about a different galaxy. What about this galaxy right here? So we said this was 5 megaparsecs away. Here's one that's about 10 megaparsecs away. It's twice as far away. But because of this linear relationship, it's also moving away from us twice as fast, right? So if we do the same calculation for this galaxy right here, it's twice as far away from us, but it's moving twice as fast. If we calculate the amount of time that it takes for that galaxy going backwards to be where we are right now, we get exactly the same number. That galaxy was where we are at the same time that that galaxy was where we are. It's twice as far away, it has twice as far to go, but it's moving twice as fast. We can take this galaxy at 15 kilometers per second, 15 megaparsecs. It's moving away from us 3 times faster, but it's 3 times further away. You get the same rewind distance for this galaxy as well. In fact, every single galaxy that falls along this line, and by that, I mean every single galaxy in the universe has the same rewind time. If you calculate how long it has taken that galaxy to get to this distance at that velocity, you get exactly the same amount of time for all of these galaxies. The universe is expanding, and we can rewind that clock. We get to a point where the universe must have begun. The universe must begin, t equals 0, must be when all of those galaxies were in exactly the same place at the same time. And so we can make that calculation. In fact, the slope of this line gives us that value, because this is, remember, velocity equals distance divided by time. Let's solve this for time. Multiply both sides by time. Divide both sides by velocity. Things cancel out over here, cancel out over here. We get t equals the distance divided by velocity. Well, what is the slope? Well, we're plotting velocity versus distance. So the slope would be rise over run, which is v over d. That's just the inverse of the slope of that line. The look back time, or the rewind time, is just the inverse of the slope. And we know what the slope is. We've already defined the slope of the Hubble law. The slope is h naught. And so the look back time, or the rewind time, is just the inverse of the Hubble law constant. That is how long you have to rewind the clock before all those galaxies are where we are now. And it is also the present age of the universe, because that's how long it's taken the universe to expand to its present size. So here it is, age of the universe in better handwriting and better font, but the same equation. Now, what do the squiggles mean? Now, I wrote an equal sign on the previous page, and I wrote squiggle equal sign here. What do I mean by squiggle equal sign? Well, what I mean by squiggle equal sign is it's about equal to. It's not exactly equal to, it's about equal to. And that's because in doing this, in making this calculation, we've made a fundamental assumption about how the universe has been expanding and how that expansion has been changing over time. Specifically, if we want to use velocity equals distance divided by time, that assumes that that velocity is going to be constant and not changing. And we know that that actually isn't the case. We know that the velocity of the recessional velocities of galaxies in the universe are changing over time. And so this isn't a perfect number, but it gives us a pretty good handle on how old the universe has to be. So with the assumption that the universe has been expanding, with the incorrect assumption that the universe has been expanding at a steady rate, this will give you the age of the universe. And even so, it actually comes pretty close to the actual age of the universe, even though that assumption isn't correct. So let's do it. What is the age of the universe? We know what the Hubble constant is. We can now calculate from the Hubble constant what the age of the universe is. Isn't that exciting? Let's do it. T equals 1 over h naught. Well, what's h naught? Well, we said it was about 72 kilometers per second per megaparsec. Great. That's fantastic. This isn't a terribly useful unit, but I can still do some equations and calculations with this. What is 1 over 72? So here I'm going to do two things. I'm going to take the unit separately from the number. So I'm going to think about the number, and I'm going to think about this also separately. So I've got a 1 over 72 for the number, and I've got a 1 over kilometers per second per megaparsec for the unit. Let me think about the number first. 1 over 72, I can just plug that into my calculator. It's 0.0139. But what are the units on that number? Well, again, it's kilometers per second per megaparsec, but it's the inverse of that. I have to take 1 over that. And so the units that are in the denominator move up to the numerator, and the kilometer stays in the denominator. And so this just becomes, the whole thing flips over, basically. And this becomes instead seconds times megaparsecs divided by kilometers. Well, that is a strange unit. But it is a unit of time, which is good. We've got seconds up here, and we've got a distance on top, and we've got a distance on bottom. But this isn't a very useful unit of time, because those units, we would like those units of distances to go away. But we can do that. We know how to make units of distances go away, because we know how many kilometers there are in a parsec. We know how many kilometers are in a megaparsec. We can just multiply by the number of kilometers in a megaparsec, and those will go away. Let me show you how that works. You can look this up, but 1 parsec is 3.09 times 10 to the 16 meters. And if you want to divide by 1,000, it's more likely we want it in kilometers. 3.09, if you divide this by 1,000, that's 10 to the 3. You just need to decrease the exponent by a factor of 3. So this is 3.09 times 10 to the 13 kilometers. Great. Well, a megaparsec is 1,000,000 parsecs. So 1 megaparsec is this number times 1,000,000, and 1,000,000 is 10 to the 6. So all I need to do is multiply this number by 10 to the 6, or raise this number by 6 by adding 6 to the exponent, and I will have the number of megaparsecs in a kilometer, 3.09 times 10 to the 19 kilometers. Or you can just plug it into Google, and Google will probably tell you exactly how many kilometers there are in megaparsecs. Anyway, that's the number. So now over here, we want to use this to get rid of the megaparsecs in kilometers. Well, I can do that. Again, this is my normal unit conversion business. If I multiply by something on top, which is the same as the thing on the bottom, I'm not changing the value of this number, but I can use that to get rid of units. And if I put kilometers on top and megaparsecs on the bottom, my units will cancel out. So I know that 1 megaparsec is equal to 3.09 times 10 to the 19 kilometers. And now my megaparsecs cancel out, my kilometers cancel out, and I'm left with seconds. So all I have to do is take this 0.0139 and multiply it by 3.09 times 10 to the 19. I'm going to do that over here. The number I get when I plug that into my calculator is 4.3 times 10 to the 17. And what are the units on that? The units on that are seconds, because it's the only thing left in my unit tree. Okay, well, that's a lot of seconds. That seems like a reasonable number, I guess. But again, seconds probably isn't the right unit to be using for this. Let's try to convert this into years. Remember how to do that. We know that there are 60 seconds in a minute. In this case, we want 60 seconds on the bottom so that the seconds will cancel out. We know that there are 60 minutes in an hour. We know that there are 24 hours in a day. We know that there are 365 days in a year. And when we multiply all those together, or divide 4.3 times 10 to the 17 by 60 by 60 by 6 by 24 by 365, we get 1.36 times 10 to the 10 years. And let me just show you that the units all cancel out. Minutes have gone away, hours have gone away, days have gone away, and the only one left is years. And so 1.36 times 10 to the 10 years. And if you know that 1 billion is 10 to the 9, this is 13.6 billion years. And that deserves a red circle around it. That is the actual age of the universe, within the squiggles, within the assumptions that we've made, which is comfortably older than the sun, for instance. We think the sun is about 5 billion years. We think the oldest globular clusters are about 11 billion years. This is a picture that can make sense and is compatible with the oldest things that we see in the universe, which is nice. Okay, we'll come back in the next video and think more about the implications of the Hubble law and what it means for the universe as a whole. See you then.